Hello, and welcome to Sleepy Engineering. In this video, we will explore the complete structure and function of all the essential parts that make up a car. From the engine to the gearbox, from the clutch to the suspension, every system and every component will be described slowly and carefully. This narration is intentionally calm and detailed. It is designed to help you relax, focus, or fall asleep. There will be no sudden sounds, no music, and no emotional tone. Only the steady voice of information guiding you through the machinery of the automobile. Now, please sit back, close your eyes if you like, and let the journey through the car and all of its parts begin. A car is one of the most complex and yet familiar machines in modern life. And to understand it fully, it is necessary to look at its structure as a whole before examining the details of its individual parts. The structure of the car can be thought of as a system in which many components are connected together, each performing a specific function, while also supporting the operation of the others. At the most basic level, a car consists of the body, the chassis, the powertrain, the suspension, the steering, the braking system, the electrical system, and the interior systems that provide comfort and control for the driver and passengers. Each of these categories is in itself composed of multiple parts, and each of those parts has a clear role that contributes to the operation of the vehicle as a complete unit. The body of the car is the outer shell that gives the vehicle its shape, provides aerodynamic efficiency, and offers protection to the occupants. It includes panels made of steel, aluminum, or in some modern cars, carbon fiber and composite materials. And it is designed to absorb impacts while also resisting corrosion and weather. The chassis is the structural framework to which all other parts are attached, often built as a rigid ladder frame or a unibody structure where the body and chassis are integrated. It ensures strength and stability and serves as the base upon which the engine, suspension, and other systems are mounted. The powertrain is the combination of components that generate and transmit power, consisting of the engine, the gearbox, the clutch or torque converter, the driveshaft, and the differential that delivers power to the wheels. Without this system, the car would not move, as it is the powertrain that converts chemical energy stored in the fuel into mechanical motion on the road. The suspension system is another crucial structural element that links the wheels to the chassis, using springs, dampers, and linkages to provide comfort, stability, and control. The suspension must allow the wheels to move up and down over bumps while keeping the tires in firm contact with the road, which is essential for both safety and performance. The steering system allows the driver to control the direction of the vehicle, translating the rotation of the steering wheel into the turning of the front wheels through a series of gears, rods, and sometimes hydraulic or electric power assistance. Closely related to steering in importance is the braking system, which provides the ability to slow down or stop the car. Modern cars use disc or drum brakes, controlled hydraulically and often supplemented with electronic systems, such as anti-lock braking, to ensure stability during sudden stops. Another layer of the structure is the electrical system, which powers lights, sensors, ignition, and many auxiliary devices. The battery, alternator, and starter motor form the core of this system. But modern cars include increasingly complex networks of wires, control units, and software that link mechanical parts with electronic intelligence. Finally, the interior of the car is a system in its own right, housing the seats, the dashboard, the climate control, and the controls that allow the driver to interact with the machine. It is where human and machine meet, making it an essential part of the structure, not only for functionality, but also for safety and comfort. By viewing the car as a combination of all these structural categories, it becomes clear that no single part exists in isolation. Every component depends on others, and the overall reliability of the car arises from the way these systems are integrated. In the following sections, we will move through these systems one by one, beginning with the engine and progressing steadily through transmission, suspension, steering, braking, and all the other elements, until the entire structure of the car and the purpose of each part is fully described. This slow and methodical exploration will reveal how thousands of components work together to create the single machine that most people recognize simply as the car. The engine is the heart of the car, the source of power that allows all other systems to function, and it has been developed over more than a century into a highly efficient and reliable machine. At its core, the engine is a device that converts chemical energy stored in fuel into mechanical energy that can turn the wheels and move the vehicle forward. The most common type of engine in cars is the internal combustion engine, which burns fuel and air inside a chamber to create controlled explosions that push pistons downward. These pistons are connected to a crankshaft that converts the up and down motion into rotational motion, and that rotation is the source of mechanical power for the car. The basic components of an engine include the block, the cylinders, the pistons, the crankshaft, the camshaft, the valves, and the head. The block is the heavy metal structure that holds the cylinders, and inside each cylinder, a piston moves up and down. The pistons are fitted with rings to seal them against the walls of the cylinders, preventing gases from leaking past and maintaining compression. The crankshaft is located at the bottom of the engine, and it rotates as the pistons move, transferring energy outward. The camshaft is responsible for controlling the opening and closing of the valves, which let air and fuel in and exhaust gases out. These valves are timed with precision to open at the correct moments, and the camshaft is usually connected to the crankshaft by a timing belt or chain to keep everything synchronized. The cylinder head sits on top of the block and contains passages for air and fuel, spark plugs for ignition, and additional valves if the design requires them. Combustion engines come in several configurations depending on how the cylinders are arranged. Inline engines place all cylinders in a single row, which makes them simple and compact. V engines place cylinders in two angled banks, creating a V shape that allows for more cylinders in a shorter length. Flat engines, sometimes called boxer engines, place the cylinders horizontally opposite each other for low vibration and a low center of gravity. The number of cylinders can vary as well, with small cars often using 3 or 4 cylinders, and performance or luxury cars using 6, 8, or even 12. Each design offers a different balance of power, smoothness, cost, and efficiency. The engine also requires several subsystems to function correctly. The intake system brings in air, sometimes compressing it with a turbocharger or supercharger to increase power. The fuel system delivers gasoline or diesel in carefully measured amounts, often using modern fuel injection for precision. The ignition system uses spark plugs in gasoline engines to ignite the fuel mixture, while diesel engines rely on compression alone to ignite the fuel. The exhaust system carries away the burnt gases, often passing them through catalytic converters and particulate filters to reduce harmful emissions. Cooling and lubrication are also essential, since the combustion process generates enormous heat and friction. Coolant circulates through passages in the engine and into a radiator where it releases heat, while oil is pumped to all moving parts to reduce wear and prevent overheating. The purpose of the engine is not only to produce power, but also to do so in a reliable, efficient, and controlled way. Modern engines are controlled by electronic systems that monitor sensors and adjust fuel, ignition, and airflow many times every second to optimize performance and emissions. In addition to internal combustion engines, electric motors are now becoming more common in cars. An electric motor works differently by using magnetic fields and electric current to produce rotation directly without combustion. These motors are often paired with batteries that store energy and power electronics that regulate delivery. Some vehicles use hybrid systems that combine an internal combustion engine with one or more electric motors, giving flexibility and efficiency. No matter the design, the engine remains the primary source of energy for the car, and understanding its components and types is the foundation for understanding the rest of the vehicle. The transmission system is the vital link between the engine and the wheels, and its purpose is to ensure that the power produced by the engine is delivered in a usable and efficient way. An engine produces power most efficiently within a certain range of speed, usually referred to as revolutions per minute or RPM, but the demands of driving require very different speeds and forces at the wheels. The transmission, also known as the gearbox, allows the car to adapt by providing different gear ratios so that the wheels can turn slowly with high force when starting or climbing a hill, and turn quickly with lower force when cruising at high speed. The gearbox itself is a mechanical assembly filled with shafts, gears, and bearings that transfer rotation from the engine to the driveshaft. In a manual transmission, the driver selects gears using a lever connected to linkages or cables, and the selected gear engages specific pairs of gears inside the gearbox. Each pair of gears has a specific size ratio, and this determines how many times the engine must turn for the wheels to turn once. A lower gear means the engine turns many times while the wheels turn slowly, providing torque for acceleration. A higher gear means the wheels turn faster for each rotation of the engine, making it efficient for steady, high-speed driving. Within the gearbox, there are components such as the input shaft, the output shaft, and the counter shaft, each carrying gears that mesh together. Synchronizers are used to match the speed of gears before they are engaged, ensuring smooth shifting without grinding. Bearings allow the shafts to spin freely with minimal friction, and seals keep lubrication inside while keeping dirt out. Automatic transmissions achieve the same purpose, but use a very different mechanism. Instead of the driver manually selecting gears, hydraulic pressure, sensors, and control systems shift gears automatically. Traditional automatic transmissions use a torque converter in place of a clutch to connect the engine to the gearbox, allowing smooth transfer of power without the driver needing to disengage gears. Planetary gear sets, made of sun gears, planet gears, and ring gears, are arranged in combinations to create different gear ratios within a compact design. Modern automatic transmissions may have 6, 8, or even 10 gears to provide both smooth acceleration and efficient cruising. In addition, there are continuously variable transmissions, or CVTs, which do not have fixed gears at all. Instead, they use a system of pulleys and a belt or chain to provide an infinite range of ratios between low and high. This allows the engine to stay at its most efficient RPM, while the car adjusts speed seamlessly. Dual clutch transmissions are another design, combining features of manual and automatic systems. They use two separate clutches for odd and even gears, allowing one gear to be engaged while the next is already prepared, creating lightning-fast shifts and improved efficiency. The transmission system also includes supporting parts such as the clutch in manual cars or the torque converter in automatics, as well as gear selectors, sensors, and control modules that monitor performance. Lubrication is essential in the gearbox, since the constant meshing of gears generates heat and friction, and gear oil is specifically designed to withstand high pressure between gear teeth. The purpose of the gearbox is not only to transmit power, but also to provide the flexibility required for different driving situations, from starting and accelerating to cruising and slowing down. Without it, the engine would either stall at low speeds or overspeed at high speeds, making the car impractical to drive. By converting the high speed, low torque output of the engine into the appropriate speed and torque for the wheels, the transmission ensures that the car can operate smoothly, efficiently, and reliably in every condition. Understanding the gearbox is essential to understanding how the car adapts the steady rhythm of the engine into the varied demands of the road. The clutch is one of the most important components in the connection between the engine and the transmission, and its purpose is to allow the driver to smoothly engage and disengage power so that gears can be changed and the car can start moving without sudden shocks. In its simplest form, the clutch is a mechanical device that connects two rotating shafts, one from the engine and one leading to the gearbox, and allows them to be temporarily separated when needed. In a manual transmission car, the clutch pedal on the floor is directly linked to the clutch mechanism, and pressing the pedal disengages the clutch, while releasing it re-engages the connection. The main parts of a typical clutch system include the flywheel, the clutch disc, the pressure plate, the release bearing, and the actuating mechanism. The flywheel is a heavy rotating plate attached to the crankshaft of the engine, and it provides a smooth surface for the clutch disc to press against. The clutch disc is a flat, circular plate lined with friction material similar to brake pads, and it sits between the flywheel and the pressure plate. The pressure plate applies force against the clutch disc, holding it firmly against the flywheel so that rotation from the engine is transferred through the disc to the transmission input shaft. When the driver presses the clutch pedal, the release bearing pushes against springs in the pressure plate, lifting it away and releasing the pressure on the clutch disc. This allows the disc to spin freely, disconnecting the engine from the gearbox and enabling the driver to change gears. Once the new gear is selected, releasing the pedal allows the pressure plate to press the disc back against the flywheel, re-establishing power transfer. The friction material on the clutch disc must provide enough grip to hold against the flywheel without slipping, while also being durable enough to withstand thousands of engagements over the life of the car. Because this material wears down with use, clutches are considered consumable components that eventually require replacement. The design of the clutch must balance smoothness with strength, since a sudden engagement would cause the car to jerk forward, while a weak grip would cause slippage and overheating. In addition to the main clutch components, there are different types of actuation systems. A cable-operated clutch uses a steel cable to pull on the release mechanism, while a hydraulic clutch uses fluid pressure created by a master cylinder and transmitted through lines to a slave cylinder near the clutch. Hydraulic systems tend to provide smoother and more consistent operation, while cable systems are simpler and cheaper to maintain. There are also more advanced designs, such as multi-plate clutches, used in motorcycles or high-performance cars, where multiple discs provide greater surface area for handling more power in a compact space. Automatic transmissions typically replace the manual clutch with a torque converter, which is a fluid coupling that transmits power smoothly without the need for a pedal. Dual clutch transmissions, however, still use clutches, but they are controlled automatically by electronics and hydraulics, allowing for extremely fast gear changes without driver input. The role of the clutch in power transfer is fundamental because it gives the driver control over how and when the engine's rotation is applied to the wheels. It allows the car to start from a stop by gradually increasing the contact between the engine and the transmission, preventing the engine from stalling. It allows gears to be changed without grinding, since the gearbox needs the input shaft to be free of torque while gears are selected. It also allows the driver to momentarily disconnect the engine when coasting or stopping. Without a clutch, the connection would be permanent, making smooth driving and gear shifting impossible. The clutch is therefore both a safety and convenience feature, giving flexibility to the operation of the car. Understanding the clutch and its role in power transfer highlights how even a single component plays a crucial part in the overall system, enabling the cooperation between engine and transmission that defines the driving experience. The driveshaft and differential are two key components in the drivetrain of a car, and together they ensure that power from the engine and transmission is effectively delivered to the wheels in a controlled and usable manner. The driveshaft is essentially a long rotating shaft that transfers torque from the transmission to the differential, and it must do so while accommodating the movement of the suspension and the distance between the gearbox and the wheels. In rear-wheel drive vehicles, the driveshaft runs along the length of the car from the transmission at the front to the differential at the rear, while in front-wheel drive vehicles, the function is performed by shorter half shafts that connect the transaxle directly to the wheels. The driveshaft is usually made of strong but lightweight materials, such as steel or aluminum, and in high-performance applications, it may be constructed from carbon fiber for strength and reduced weight. It is supported by universal joints or constant velocity joints at its ends, which allow it to flex and transmit power even when the angles of connection change as the suspension moves up and down or the wheels turn. These joints are crucial because without them, the rigid shaft would bind or break whenever the car encountered bumps or turns. Along with transmitting power, the driveshaft must remain balanced, since even small imbalances at high speed can cause vibrations, noise, and wear on bearings. Balance weights are often welded onto the shaft to ensure smooth rotation. The differential, located at the end of the driveshaft, is a gear assembly that distributes power to the wheels while allowing them to rotate at different speeds. This is essential because when a car turns, the outer wheel must travel a greater distance than the inner wheel, and therefore the two wheels cannot rotate at the same speed. Without a differential, both wheels would be forced to spin together, causing skidding, tire wear, and difficulty in handling. The differential solves this by using a set of bevel gears or planetary gears to split torque between the two wheels, allowing them to rotate independently while still being powered. Inside a standard open differential, the driveshaft turns a pinion gear, which engages a ring gear attached to the differential case. Within the case, small spider gears connect to side gears attached to each axle shaft. This arrangement allows torque to be sent to both wheels, while permitting speed differences between them. One limitation of the open differential is that it tends to send more torque to the wheel with less traction, which can be problematic on slippery surfaces. To address this, limited slip differentials use clutches, cones, or viscous fluids to provide resistance and send more torque to the wheel with grip. Locking differentials go further by mechanically locking both wheels together when needed, useful in off-road vehicles. Modern cars may also use electronic systems that mimic the effect of a limited slip differential by applying brakes to a slipping wheel, ensuring torque goes to the other side. In front-wheel drive cars, the differential is usually built into the transaxle, combining transmission and differential into a single compact unit. In rear-wheel drive cars, it is a separate assembly at the rear axle. All-wheel drive cars may use multiple differentials, including a center differential that splits torque between front and rear axles, and additional limited slip or locking units to handle complex traction situations. The driveshaft and differential must also be lubricated and cooled, since the gears inside experience high pressure and friction. Differential housings contain gear oil that is thicker than engine oil, designed to cling to gears and bearings even under heavy loads. Some high-performance cars even have cooling fins or pumps to manage heat in the differential. The overall purpose of the driveshaft and differential is to ensure that power created by the engine and modulated by the transmission and clutch is finally delivered to the wheels in a way that matches the demands of real driving conditions. Without the driveshaft, there would be no connection between front and rear sections of the drivetrain, and without the differential, the car would struggle to turn properly. Together, they form an indispensable link in the chain of motion that defines the automobile. The fuel system of a car is responsible for storing fuel, delivering it to the engine, and ensuring that it is mixed with air in the precise proportions required for combustion. Without the fuel system, the engine would have no source of energy, and the car would remain motionless. The major components of this system are the fuel tank, the fuel pump, the fuel lines, the fuel filter, and the injection system, or carburetor, depending on the age and design of the vehicle. The fuel tank is the storage container, mounted usually at the rear of the car, designed to safely hold gasoline or diesel while protecting it from leaks, impacts, and evaporation. Modern tanks are often made from high-strength plastic that resists corrosion and reduces weight, though older vehicles used metal tanks. Inside the tank are baffles that reduce sloshing when the car moves or corners, and most tanks also contain a fuel level sensor that sends information to the gauge on the dashboard. The fuel pump is the next essential component, drawing fuel from the tank and pushing it through the lines toward the engine. In older cars, a mechanical pump driven by the engine was common, but modern cars use electric pumps mounted inside the fuel tank. Electric pumps provide consistent pressure and help prevent vapor lock, while also being cooled by the surrounding fuel. The pump pushes fuel through the fuel lines, which are reinforced tubes designed to withstand pressure and resist leaks. Along the way, the fuel passes through a filter that removes dirt, rust particles, and other impurities that could damage delicate injectors or clog passages. The filtered fuel then reaches the injection system, which is where it is metered and delivered into the engine. In the past, most cars used carburetors, devices that relied on airflow to draw fuel into the intake stream. Carburetors were relatively simple but imprecise, often leading to inefficient combustion and higher emissions. Today, nearly all vehicles use fuel injection, which precisely sprays fuel into the intake manifold or directly into the combustion chamber in carefully timed pulses. There are several types of injection systems. Port fuel injection sprays fuel into the intake ports just ahead of the intake valves, allowing it to mix with air before entering the cylinder. Direct injection sprays fuel directly into the combustion chamber, providing even greater control of timing and mixture. Both systems are controlled by an electronic control unit, or ECU, that monitors sensors measuring oxygen in the exhaust, throttle position, air temperature, engine speed, and many other parameters. The ECU constantly adjusts injection timing and amount to maintain the ideal air-fuel ratio, usually around 14.7 parts of air to 1 part of fuel for gasoline engines, known as the stoichiometric ratio. Diesel engines operate differently, using high compression to ignite the fuel, but they also rely on a precise injection system that delivers fuel at extremely high pressures to achieve efficient combustion. The fuel system must also manage vapors, since gasoline easily evaporates and creates fumes that are both hazardous and polluting. Modern cars are equipped with evaporative emission control systems, which capture vapors from the tank and store them in a charcoal canister until they can be burned in the engine. Safety is another major consideration. With tanks designed to resist punctures and fuel pumps that shut off automatically in the event of a crash to prevent leaks or fires. The overall purpose of the fuel system is to ensure that the engine always receives the correct amount of clean fuel at the right pressure and in the right form for combustion. It allows the driver to simply turn the key or press a button and have the engine start reliably, idle smoothly, and respond instantly to throttle input. The evolution from simple carburetors to sophisticated direct injection systems illustrates how much engineering has gone into maximizing efficiency, power, and cleanliness in the automobile. Without the fuel system, the energy stored in liquid fuel would remain untapped, but with it, the engine is able to perform the controlled explosions that create motion and power the entire car. The exhaust system of a car is responsible for carrying away the gases produced during combustion, reducing noise, and minimizing harmful emissions before they are released into the atmosphere. When fuel burns inside the engine, it creates a mixture of gases that include carbon dioxide, water vapor, nitrogen, carbon monoxide, hydrocarbons, and nitrogen oxides. Without a proper exhaust system, these gases would escape directly into the air under high pressure and at high temperature, creating both noise and pollution. The exhaust system begins at the exhaust manifold, which is bolted directly to the cylinder head and collects gases from each cylinder. The manifold channels these gases into a single pipe, and it must withstand extreme heat since temperatures can exceed several hundred degrees Celsius. From the manifold, the gases flow into pipes that carry them toward the back of the car, passing through a series of components designed to reduce pressure, noise, and emissions. One of the first of these components is often the catalytic converter, a device filled with a ceramic honeycomb coated with precious metals such as platinum, palladium, and rhodium. As exhaust gases pass through, chemical reactions occur that convert carbon monoxide into carbon dioxide, hydrocarbons into carbon dioxide and water, and nitrogen oxides into nitrogen and oxygen. This drastically reduces the toxicity of emissions and is one of the most important innovations in automotive engineering. Modern cars may also include additional emission controls, such as particulate filters, especially in diesel engines, which capture soot particles and periodically burn them off to keep the filter clear. After emission control devices, the exhaust gases pass through a muffler, which reduces noise by using chambers, baffles, and sound-absorbing materials to cancel out the pressure waves created by combustion. Without a muffler, the sound of an engine would be unbearably loud, since each cylinder firing creates a sharp pulse of high-pressure gas. The muffler allows a car to operate at a noise level acceptable for everyday use, while still allowing free flow of gases. Some systems also include a resonator, which fine-tunes the exhaust sound and can reduce certain frequencies of noise. The exhaust system must be carefully designed to balance noise reduction, emission control, and engine performance. Restricting the flow of gases too much would reduce efficiency and power, while insufficient control would increase pollution and noise. Engineers design the diameter and length of exhaust pipes, the placement of converters and mufflers, and even the material of construction to optimize these factors. Stainless steel is commonly used because it resists corrosion from moisture and chemicals present in exhaust gases. In performance cars, the exhaust system is often tuned to reduce back pressure and sometimes deliberately designed to produce a distinctive sound. In hybrid and electric cars, the role of the exhaust system is minimal or non-existent, since no combustion takes place. But in internal combustion vehicles, it remains an essential part of the overall design. Emission control extends beyond the catalytic converter and filter, as modern cars use oxygen sensors placed in the exhaust stream to monitor the composition of gases. These sensors send signals to the engine control unit, which adjusts the fuel mixture to ensure combustion remains as clean and efficient as possible. This closed-loop system allows continuous regulation and is critical for meeting environmental regulations. Some vehicles also include exhaust gas recirculation systems, which route a portion of exhaust gases back into the intake to lower combustion temperatures and reduce nitrogen oxide formation. The exhaust system is therefore both a safety device by directing hot gases away from the cabin and an environmental safeguard by reducing pollutants. Its presence allows cars to meet strict legal requirements while still providing the power and performance expected by drivers. The development of advanced catalytic converters, filters, and sensors shows how much effort has been invested in minimizing the environmental impact of automobiles. Without an exhaust system, the car would be noisy, polluting, and unpleasant to drive. But with it, the operation becomes controlled, safe, and compatible with modern expectations of comfort and responsibility. The cooling system of a car is one of the most essential subsystems, because the combustion process inside the engine produces extreme amounts of heat that must be controlled to prevent damage and maintain efficient operation. Every time fuel burns in the cylinders, it releases thermal energy, and much of this energy is not converted into useful motion, but remains as heat within the metal components of the engine. If this heat were not removed, the engine would quickly overheat, leading to warped parts, seized pistons, or even catastrophic failure. The cooling system is designed to absorb this heat, transport it away from the engine, and release it into the air in a controlled manner. The central component of the cooling system is the radiator, a heat exchanger, usually located at the front of the vehicle, where it can receive airflow as the car moves. The radiator consists of a network of thin tubes and fins that maximize surface area so that heat from the coolant fluid can transfer into the surrounding air. A cooling fan is often mounted behind the radiator to draw air through the fins when the car is stationary or moving slowly, ensuring consistent cooling in all conditions. The coolant itself is a liquid mixture, usually water combined with antifreeze, that circulates continuously through the engine and radiator. Antifreeze is typically made from ethylene glycol or propylene glycol, and it not only lowers the freezing point of the liquid, but also raises the boiling point, allowing the system to operate safely in both winter and summer. The coolant absorbs heat from passages inside the engine block and cylinder head, then flows through hoses into the radiator where the heat is released. After cooling, the liquid returns to the engine to repeat the cycle. This circulation is driven by a water pump, usually powered by a belt connected to the engine crankshaft, although some modern vehicles use electric pumps for more precise control. The water pump ensures constant movement of coolant, preventing hot spots and maintaining even temperatures throughout the engine. A thermostat regulates the flow of coolant by opening and closing based on temperature. When the engine is cold, the thermostat remains closed, allowing the engine to warm up quickly by keeping coolant within the block. Once the coolant reaches the proper operating temperature, the thermostat opens, allowing fluid to pass through the radiator for cooling. This balance ensures the engine runs neither too cold nor too hot, which is important for efficiency, emissions, and durability. The cooling system also includes an expansion tank or reservoir, which provides space for coolant to expand as it heats and prevents excessive pressure within the system. Pressure caps maintain the system at a higher pressure than the atmosphere, raising the boiling point of the coolant and allowing it to absorb more heat without vaporizing. In addition to liquid cooling, many engines rely on oil cooling as well, since engine oil not only lubricates moving parts, but also carries away heat. Some vehicles include oil coolers, which function like miniature radiators specifically for engine or transmission oil. Air cooling has been used in the past, with engines surrounded by fins and cooled directly by airflow. But liquid cooling with a radiator has become the standard due to better control and efficiency. The cooling system must also consider the passenger cabin, as heat from the coolant is diverted through a heater core, another small radiator located inside the dashboard. Air blown across this heater core provides warm air for defrosting and comfort. This shows how the cooling system not only protects the engine, but also contributes to the interior environment of the car. Maintenance of the cooling system is crucial, as low coolant levels, clogged radiators, or broken pumps can quickly lead to overheating. Regular replacement of coolant prevents corrosion and buildup inside the system, while inspection of hoses and belts ensures reliable operation. The purpose of the cooling system and radiator is therefore to maintain the delicate balance between heat and performance, keeping the engine in the optimal temperature range. Without this system, the engine would not survive even a few minutes of operation, but with it, the car can run smoothly for thousands of hours, efficiently and safely turning fuel into motion while keeping temperatures under control. The lubrication system of a car is essential for reducing friction, cooling moving parts, and ensuring that the engine operates reliably over long periods of time. Inside an engine, there are hundreds of surfaces that move against each other at high speeds, including pistons sliding inside cylinders, camshafts turning against bearings, crankshafts rotating in journals, and valves opening and closing repeatedly. Without lubrication, the metal surfaces would grind together, generating heat, wear, and eventually failure. Engine oil provides a thin film that separates these surfaces, allowing them to move smoothly, while also carrying away heat and contaminants. The oil is stored in a sump or oil pan located at the bottom of the engine, and from there it is drawn up by the oil pump. The pump is driven by the engine, usually through gears or a chain, and it pressurizes the oil before sending it through passages called oil galleries. These galleries distribute oil to every critical part of the engine, from the crankshaft bearings to the camshaft lobes. The pressurized oil not only lubricates, but also cushions moving parts, reducing noise and vibration. Along its path, the oil passes through a filter, which removes dirt, carbon deposits and microscopic metal shavings that accumulate as the engine runs. The oil filter is typically a replaceable cartridge with fine paper or synthetic fibers that trap particles while allowing clean oil to pass through. Without filtration, the contaminants would circulate and cause wear on precision components. The oil also plays a vital role in cooling, since it absorbs heat from pistons, bearings, and other hot surfaces before returning to the sump where the heat can dissipate. In high-performance engines, there may be additional oil coolers, small radiators dedicated to lowering oil temperature, ensuring it remains within an optimal range. The lubrication system must maintain the correct oil pressure at all times, and sensors monitor this pressure to warn the driver if levels drop dangerously low. Too little oil or insufficient pressure can cause the film of lubrication to break down, leading to direct contact between surfaces and rapid engine damage. Too much pressure can also be harmful, so pressure relief valves are included to regulate the system. Different engines use different oil circulation methods. The most common is the wet sump system, where oil is stored directly in the pan under the engine. A less common but advanced design is the dry sump system, used in racing and high-performance cars, where oil is stored in a separate tank and pumped into the engine. This prevents oil starvation during high-speed cornering and allows the engine to sit lower in the chassis. Engine oil itself is carefully engineered with base oils and additives. The viscosity of oil, often indicated by ratings such as 5W30 or 10W40, determines how easily it flows at different temperatures. Additives include detergents to keep passages clean, anti-wear agents to protect surfaces, and antioxidants to prevent breakdown under heat. Over time, oil degrades and becomes contaminated, which is why regular oil changes are required to maintain engine health. The lubrication system also extends beyond the engine, since transmissions, differentials, and other components also rely on specialized oils or fluids for smooth operation. Automatic transmissions use transmission fluid that not only lubricates but also acts as a hydraulic medium for gear changes. Differentials use heavy gear oil designed to handle high pressure between gears. Each system has its own fluid requirements, and using the wrong type can cause serious damage. The overall purpose of the lubrication system is to ensure longevity, efficiency, and reliability by reducing friction and managing heat. It allows the engine to run at high speeds for hours without seizing, and it minimizes wear so that cars can travel hundreds of thousands of kilometers before major overhauls are needed. Without lubrication, the modern internal combustion engine would not be possible. But with it, the complex interaction of moving parts becomes sustainable, smooth, and efficient. The circulation of oil may be invisible to most drivers, but it is the silent guardian that keeps the heart of the car beating steadily day after day. The suspension system of a car is designed to manage the connection between the wheels and the chassis, providing comfort, stability, and control in every driving condition. When a car travels over uneven roads, bumps, or potholes, the suspension absorbs the energy of these impacts and prevents them from being transmitted directly to the passengers or to the delicate mechanical components of the vehicle. At the same time, it ensures that the tyres remain in consistent contact with the road surface, which is essential for traction, steering, and braking. The suspension is therefore a compromise between comfort and performance, needing to be soft enough to cushion the ride, but firm enough to keep the car stable and predictable. The main components of the suspension system include springs, shock absorbers or dampers, control arms, bushings, stabilizer bars, and linkages that connect everything together. Springs are the fundamental elements that support the weight of the car and compress when a wheel encounters a bump. Several types of springs are used in automotive design, including coil springs, leaf springs, torsion bars, and air springs. Coil springs, which are simple spirals of steel, are the most common in modern cars because they are compact and reliable. Leaf springs, long strips of layered steel, are often found in trucks because they can carry heavy loads. Torsion bars use twisting resistance of a steel rod, while air springs use compressed air inside rubber bellows for adjustable comfort. Springs alone would allow the car to bounce uncontrollably after each bump, so shock absorbers are paired with them to dampen motion. A shock absorber is a hydraulic cylinder filled with oil or gas, and as it compresses or extends, it forces fluid through valves, dissipating energy as heat. This controlled resistance prevents the car from oscillating and ensures that after a bump, the wheel quickly returns to stable contact with the road. Modern cars often use struts, which combine a shock absorber and a coil spring into one compact unit, saving space and reducing weight. Control arms are hinged links that connect the wheels to the chassis and allow up and down movement while controlling alignment. They are usually fitted with rubber or polyurethane bushings that absorb vibration and allow slight flexibility. Stabilizer bars, also known as anti-roll bars, connect opposite sides of the suspension and resist body roll when the car turns. Without stabilizer bars, a car would lean excessively in corners, reducing stability and comfort. Suspension designs vary depending on the vehicle. Independent suspension allows each wheel to move separately, improving comfort and handling, and is common on modern passenger cars. Solid axle suspension connects both wheels with a rigid beam, often used on trucks for strength and durability. Multi-link suspension uses several arms to precisely control wheel movement, offering both comfort and performance, but at higher cost and complexity. Air suspension and adaptive suspension systems add electronic control, adjusting stiffness or ride height according to conditions. The suspension system must also be durable, since it constantly endures impacts, loads, and stresses. Components such as bushings and ball joints wear over time and require replacement to maintain proper function. Alignment of the suspension is also critical, as incorrect angles of camber, caster, or toe can lead to uneven tyre wear and poor handling. The importance of the suspension system extends beyond comfort, because safety relies on it as well. A car with worn shocks or broken springs may lose tyre contact with the road, reducing braking ability and steering response. In emergency maneuvers, the suspension helps distribute weight evenly so that all tyres can grip effectively. Shock absorbers, in particular, are vital for ensuring that the tyres do not bounce and lose traction. The suspension also plays a role in the driving experience, as a well-designed system can make a car feel stable, predictable, and enjoyable, while a poorly designed or worn suspension can make driving tiring and unsafe. Overall, the suspension system and shock absorbers form the essential bridge between the rigid chassis and the unpredictable surface of the road, managing forces and motion so that the car can deliver both comfort and control. Without them, the ride would be harsh, unstable, and dangerous. but with them, the car becomes capable of handling the variety of surfaces and situations encountered in everyday driving. The steering mechanism of a car is the system that allows the driver to control the direction of the vehicle by turning the front wheels in response to input from the steering wheel. At its core, the steering system translates the rotational movement of the driver's hands into the angular movement of the wheels, and it must do so with accuracy, reliability, and minimal effort. The basic components of a steering system include the steering wheel, the steering column, the steering gear, the linkages such as tie rods, and the front wheel assemblies. When the driver turns the steering wheel, this motion is transferred down the steering column, which is a shaft that often includes universal joints to account for angles and collapsible sections for safety in a crash. At the bottom of the column, the motion reaches the steering gear, which is the mechanism that converts the rotational input into lateral movement. The most common steering gear design in modern cars is the rack and pinion system. In this design, the end of the steering column has a small pinion gear that meshes with a flat rack gear, and when the pinion rotates, it moves the rack sideways. The rack is connected to tie rods that push or pull the steering knuckles attached to the front wheels, turning them left or right. Rack and pinion steering is compact, precise, and provides good feedback to the driver, which is why it is widely used. Another traditional system is recirculating ball steering, where the column rotates a worm gear that moves a sector gear through ball bearings. This system is more robust and was once common in trucks and larger vehicles, though it is now less common in passenger cars. To reduce the physical effort required to turn the wheels, especially at low speeds, power steering is added to nearly all modern vehicles. Power steering uses hydraulic or electric assistance to amplify the driver's input, making it possible to steer with minimal force while still maintaining control. In hydraulic power, steering a pump driven by the engine pressurizes fluid, which is directed through valves to assist the movement of the rack or gear when the driver turns the wheel. This provides strong and smooth assistance, but it consumes some engine power and requires maintenance of fluid levels and hoses. Electric power steering has become more common in recent years, using an electric motor mounted on the steering column or rack to provide the necessary force. This system is more efficient since it only draws power when needed, and it also allows integration with electronic control systems such as lane keeping assist and automatic parking. Some cars use electro-hydraulic systems that combine elements of both. Regardless of the method, the principle remains the same: to reduce the effort required while preserving the connection between driver and road. The steering mechanism also includes geometry considerations such as caster, camber, and toe angles, which determine how the wheels align and return to center after a turn. Proper steering geometry ensures stability, reduces tire wear, and gives predictable handling. Components such as tie rod, ends, and ball joints allow the system to move freely while remaining strong enough to handle forces from the road. Over time, these parts can wear, leading to looseness in the steering or uneven tire wear, which is why regular inspection and alignment are necessary. Safety is also an integral part of steering design. The steering column is built to collapse in a collision, reducing the risk of injury to the driver. Modern systems are also integrated with electronic stability control, which can apply slight adjustments to help maintain direction during skids or emergency maneuvers. The overall purpose of the steering mechanism and power steering is to give the driver precise and effortless control over the car's path. Without steering, the car would not be able to navigate turns or avoid obstacles, and without assistance, the force required would make driving exhausting and impractical. Together, they form a system that combines mechanical simplicity with advanced technology, ensuring that the connection between human and machine is both safe and effective. The brake system of a car is one of the most important safety features, as it allows the driver to slow down or stop the vehicle reliably under a wide range of conditions. At its simplest, the brake system converts the kinetic energy of the moving car into heat energy through friction, and it must do this repeatedly, predictably, and without failure. The main types of brakes used in automobiles are disc brakes and drum brakes, each with its own design and characteristics. And most modern vehicles also include electronic systems such as ABS or anti-lock braking systems to further enhance safety. Disc brakes are the most common in modern cars, especially on the front wheels, and they consist of a metal disc called a rotor that is attached to the wheel hub. A caliper containing one or more pistons squeezes brake pads against the rotor when the driver presses the brake pedal, creating friction that slows the wheel. The system is operated hydraulically, with brake fluid transmitting force from the pedal to the caliper. Disc brakes are highly effective because they dissipate heat quickly, resist fading under repeated use, and provide consistent stopping power in both dry and wet conditions. Drum brakes, which are older in design, use a hollow drum attached to the wheel. Inside the drum are brake shoes lined with friction material that press outward against the inner surface of the drum when the pedal is applied. The hydraulic force expands the shoes and creates friction that slows the drum and the wheel. Drum brakes are less efficient at cooling and more prone to fade, but they are cheaper to manufacture and can provide strong braking force at lower cost. For this reason, they are still used on the rear wheels of some small or budget cars where braking demands are lower. Regardless of whether disc or drum brakes are used, the fundamental principle is the same. Hydraulic pressure multiplies the driver's input and applies it to friction materials that slow the rotation of the wheels. Brake fluid is a key part of this system, and it must withstand high temperatures without boiling, since boiling would create vapor bubbles that compress instead of transmitting pressure. For this reason, brake fluid requires periodic replacement to maintain safety. Modern braking systems also incorporate additional technologies. One of the most significant is ABS, or anti-lock braking, which prevents the wheels from locking during hard braking. When a wheel locks, it stops rotating while the car is still moving, causing a skid and loss of steering control. ABS uses sensors at each wheel to monitor rotation, and if it detects a wheel beginning to lock it, rapidly reduces and reapplies brake pressure many times per second. This pulsing action keeps the wheel rotating just enough to maintain traction while still slowing the car as quickly as possible. The driver feels this as a vibration in the brake pedal, and it allows steering to remain functional even under maximum braking effort. Beyond ABS, many vehicles also use electronic brake force distribution, which adjusts braking between front and rear wheels depending on load, and brake assist systems that apply full braking pressure in emergencies, even if the driver does not press hard enough. Parking brakes, sometimes called emergency brakes, form another part of the system. Traditionally, these are mechanical levers that apply the rear brakes through cables, but many modern cars now use electronic parking brakes that engage with the push of a button. Regardless of design, their purpose is to hold the car stationary when parked or provide backup braking in rare situations. Heat management is an ongoing challenge in brake design, since converting the energy of a fast-moving car into heat generates extreme temperatures. Ventilated discs, drilled rotors, and performance pads are used in some vehicles to handle these conditions. Brake systems must also be inspected regularly, as pads and shoes wear down with use, rotors can warp, and hydraulic components can leak. The purpose of the brake system is ultimately to give the driver confidence and control, ensuring that the car can always be stopped safely. Without it, even the most powerful engine or advanced suspension would be meaningless, because safety depends above all on the ability to slow down and stop when required. The electrical system of a car is the network that provides power for starting the engine, operating lights and accessories, and controlling the many electronic systems that are now standard in modern vehicles. At the center of this system are three critical components: the battery, the alternator, and the starter motor, which work together to ensure that electrical energy is always available when needed. The battery is the storage unit that holds electrical energy in chemical form, ready to be released when the ignition is switched on. Car batteries are typically lead-acid types, consisting of plates of lead and lead dioxide submerged in an electrolyte solution of sulfuric acid. Through chemical reactions, the battery can release electrons, producing a voltage of about 12 volts, which is the standard for most automotive systems. The battery provides the initial surge of electricity required to power the starter motor and ignite the engine, and it also powers systems when the engine is off, such as interior lights or the radio. However, the battery is not designed to provide continuous energy during driving, and that is the role of the alternator. The alternator is a generator driven by a belt connected to the engine's crankshaft. Inside the alternator, a rotor spins within a stator, producing alternating current through electromagnetic induction. This alternating current is then converted to direct current by a rectifier so that it can be used by the car's electrical circuits and to recharge the battery. The alternator ensures that while the engine runs, all electrical systems, including headlights, windshield wipers, climate controls, and electronic control units, receive steady power, and that the battery remains charged for the next start. The third main component, the starter motor, is a powerful electric motor that engages with the engine's flywheel to crank it at sufficient speed to begin combustion. When the driver turns the key or presses the start button, current flows from the battery through a solenoid to the starter motor. The solenoid also pushes a small gear on the starter shaft into contact with the flywheel, and as the motor spins, it turns the engine over until it can run on its own power. Once the engine starts, the starter gear disengages automatically. Together, these three parts create a cycle in which the battery powers the starter to crank the engine. The alternator then recharges the battery and powers the car while running, and the system remains ready for the next start. Beyond these primary components, the electrical system also includes fuses, relays, and wiring harnesses that distribute power safely throughout the vehicle. Fuses protect circuits from overload by braking if current exceeds safe levels, while relays act as electrically operated switches that allow small control signals to activate larger currents. The ignition system, which includes spark plugs, coils, and control modules, is another key part of the electrical network, responsible for igniting the air-fuel mixture in gasoline engines. In modern vehicles, the electrical system has expanded far beyond these basics. Electronic control units manage everything from engine performance to stability control. Sensors monitor conditions across the car, and infotainment systems provide communication and entertainment. Many cars also have multiple batteries or high-voltage packs in hybrid and electric designs. Yet the traditional 12-volt system, with its battery, alternator, and starter motor, remains the foundation upon which all other systems rely. Maintenance of the electrical system is vital, since a weak battery, faulty alternator, or worn starter motor can leave a car unable to start or operate properly. Regular checks of battery charge, belt condition, and electrical connections ensure reliability. The purpose of the electrical system is not just to start the engine, but to support every modern convenience and safety feature, from headlights to airbags, making it one of the most indispensable networks within the automobile. The interior systems of a car are the collection of components and technologies that connect the driver and passengers to the machine, making the vehicle not only functional, but also comfortable and usable. At the center of the interior is the dashboard, which provides information, controls, and displays that allow the driver to monitor the condition of the car and operate its systems. Traditional dashboards featured analog gauges such as a speedometer, tachometer, fuel gauge, and temperature gauge, each with mechanical needles and simple backlighting. Modern dashboards often incorporate digital displays, liquid crystal screens, and fully programmable instrument clusters that can show everything from navigation maps to tire pressure readings. Regardless of format, the purpose of the dashboard remains the same: to present clear and reliable information about the status of the vehicle in real time. Alongside the dashboard is the center console, which houses controls for audio, climate, and often gear selection in automatic cars. The arrangement of switches, knobs, and touchscreens is carefully designed for ergonomics, ensuring the driver can reach and operate them without distraction. Another major interior system is the HVAC unit, which stands for heating, ventilation, and air conditioning. This system manages the flow and temperature of air inside the cabin, ensuring comfort in all weather conditions. Heating is provided by diverting hot coolant from the engine through a heater core, a small radiator located inside the dashboard. Air blown across this core warms up and is directed into the cabin, providing both comfort and defrosting for windows. Ventilation is controlled by fans and ducts that distribute air evenly, while air conditioning relies on a compressor, condenser, and evaporator to remove heat and humidity from the air, cooling it before it enters the cabin. The HVAC system also includes filters that remove dust and pollen, improving air quality for passengers. Beyond these essential systems, modern cars include numerous comfort features designed to enhance the experience of driving or riding. Seats are no longer simple padded surfaces, but often incorporate adjustable supports, heating, cooling, and even massage functions in higher-end models. Power-adjustable seats allow drivers to find the ideal position at the push of a button, while memory functions store preferences for multiple users. Steering wheels may also be heated, adjustable in tilt and reach, and fitted with buttons for controlling audio, cruise control, and phone calls. Infotainment systems are now a central part of the interior, integrating navigation, communication, and entertainment into a single interface. Touchscreens, voice recognition, and smartphone connectivity allow seamless control, though many cars retain physical buttons for critical functions to maintain usability while driving. Sound systems range from basic radios to premium multi-speaker setups designed for high-quality audio reproduction. Lighting within the interior has also evolved, with ambient lighting providing a pleasant atmosphere and practical illumination, aiding visibility at night. Safety is closely tied to interior systems as well, since airbags are integrated into the dashboard, steering wheel, and seats, and seatbelt mechanisms are built into the structure. Interior sensors detect occupancy and adjust deployment accordingly. Rear-view cameras, parking sensors, and heads-up displays projecting information onto the windshield all contribute to both convenience and safety. Storage compartments, cup holders, and folding seats are smaller but still significant comfort features, making the interior more practical for daily use. Even materials play an important role, with fabrics, leathers, plastics, and trims chosen to balance durability, aesthetics, and tactile comfort. Climate control zones allow different passengers to set individual preferences, and advanced noise insulation reduces outside sounds, creating a quieter cabin. Altogether, the interior systems transform the car from a simple machine into a livable space, bridging the gap between mechanical function and human comfort. Without them, driving would be tiring and unpleasant, but with them, the car becomes an environment tailored to both control and relaxation. The safety systems of a car are designed to protect occupants in the event of a collision and to reduce the likelihood of injury or death. Among the most important of these systems are airbags, seatbelts, and crash structures, which together form a layered approach to safety. Seatbelts are the oldest and most fundamental of these features, having been widely adopted in the mid-20th century and saving countless lives since then. A seatbelt restrains the occupant during sudden deceleration, preventing them from being thrown forward into the dashboard, steering wheel, or windshield. The basic three-point seatbelt, found in nearly all modern vehicles, consists of a lap belt and a shoulder belt, combined into one continuous strap, anchored at 3 points to the car's structure. This design spreads the forces of impact across the pelvis and chest, which are stronger areas of the body, reducing the risk of serious injury. Modern seatbelts also incorporate retractors with locking mechanisms that allow the belt to extend and retract freely during normal movement, but lock in place instantly during sudden deceleration. Pretensioners are often added, which use small explosive charges or electric motors to tighten the belt in the first milliseconds of a crash, removing slack and securing the occupant firmly against the seat. Load limiters are also used to release a small amount of belt webbing under extreme force, preventing chest injuries by reducing peak loads. Airbags complement seatbelts by providing a cushion between the occupant and the hard surfaces of the car during a collision. Airbags are fabric bags folded inside compartments in the steering wheel, dashboard, seats, or pillars, and they are triggered by sensors that detect rapid deceleration. When a crash is detected, an inflator ignites a gas-generating chemical, producing nitrogen or another gas that fills the bag in less than 1/10 of a second. The bag inflates rapidly to absorb energy and reduce the impact on the occupant, then quickly deflates through vents to avoid suffocation and allow movement. Modern vehicles may have multiple airbags, including frontal airbags for the driver and passenger, side airbags for the torso, curtain airbags that deploy from the roof to protect heads in side impacts, and even knee airbags or center airbags between occupants. These systems are carefully timed and positioned to provide maximum protection in different crash scenarios. Crash structures are the third major element, and they are built into the design of the car itself. The passenger cell, or safety cage, is a rigid structure made of high-strength steel designed to remain intact during a crash, maintaining survival space for occupants. Around this cage are crumple zones, which are areas of the car deliberately engineered to deform and absorb energy during a collision, by allowing controlled deformation at the front and rear. Crumple zones slow down the deceleration experienced by occupants, reducing the forces on their bodies. Doors, pillars, and floors are reinforced to resist intrusion, while roofs are tested for rollover strength. Crash structures must balance strength with energy absorption, ensuring that the impact is managed without compromising the interior space. Safety systems also work with active technologies that aim to prevent crashes in the first place, such as electronic stability control, anti-lock brakes, and traction control. But the passive systems of seatbelts, airbags, and crash structures remain the last line of defense when a collision occurs. Together, they represent decades of engineering and testing, guided by crash test data and safety regulations, to provide the best possible protection. The purpose of these systems is not only to save lives, but also to give drivers and passengers confidence that in the worst circumstances, they are not unprotected. Without seatbelts, airbags, and crash structures, the consequences of accidents would be far more severe. But with them, the modern car is one of the safest forms of transport available. The integration of electronics into cars has transformed the automobile from a purely mechanical device into a sophisticated network of sensors, controllers, and software working together with traditional components. In the early decades of motoring cars, relied almost entirely on mechanical and hydraulic systems. But as technology advanced, electronics were gradually added first to ignition systems and radios, then to fuel injection and emission controls, and now to almost every function of the vehicle. At the heart of this integration is the Electronic Control Unit, or ECU, which is essentially a small computer programmed to monitor sensors and adjust actuators in real time. Modern cars often contain dozens of ECUs dedicated to specific tasks, such as engine management, transmission control, braking, airbags, stability systems, climate control, and even seat adjustment. These units communicate over networks such as the CAN bus, exchanging data so that the car functions as a coordinated whole. For example, when the driver presses the brake pedal, the braking ECU not only applies hydraulic pressure, but also communicates with the stability control ECU to prevent skidding, while the transmission ECU may downshift to aid deceleration. Sensors are the foundation of electronic integration, and they measure everything from wheel speed and throttle position to cabin temperature, ambient light, and even driver attention. Cameras, radar, and ultrasonic sensors provide information for advanced driver assistance systems such as lane keeping, adaptive cruise control, and automatic emergency braking. Actuators then carry out the commands of the ECUs, whether by adjusting fuel injection timing, changing gear ratios, applying brake pressure, or moving mirrors and seats. The result is a vehicle that responds not just mechanically, but also intelligently to its environment and to the driver's inputs. Electronics also extend to entertainment and communication, with infotainment systems integrating navigation, smartphones, internet connectivity, and voice control. Displays have replaced many traditional buttons and gauges, allowing customization and real-time updates. While these may appear to be luxuries, they are also tied into safety, as navigation systems provide warnings, rear cameras assist in parking, and communication systems allow hands-free operation of phones. The integration of electronics has paved the way for hybrid and electric cars, where the management of high-voltage batteries, electric motors, and regenerative braking requires precise electronic control that would be impossible with purely mechanical systems. In such vehicles, electronics balance energy flow, monitor cell temperatures, and optimize efficiency. Looking to the future, electronics will continue to define the evolution of cars. Autonomous driving technologies rely on powerful computers processing data from LiDAR, radar, cameras, and GPS to make driving decisions. Vehicle-to-vehicle communication is being developed to allow cars to share information about traffic, hazards, and road conditions, increasing safety and efficiency. Over-the-air updates now allow manufacturers to change software and add features after a car has been sold, much like smartphones, meaning that the function of a vehicle can improve over time. With increased electronic integration come challenges as well, such as cybersecurity, reliability, and the need for standardized protocols to ensure compatibility between systems. Engineers must design redundant safety systems to ensure that if one electronic component fails, others can take over and maintain control. Despite these challenges, the direction is clear. Electronics are no longer an accessory, but a central aspect of automotive engineering. The future of car systems will likely see even deeper integration, where artificial intelligence manages not only mechanical functions, but also predicts maintenance needs, adapts to driver preferences, and communicates with infrastructure such as smart traffic lights. The purpose of electronics in cars is to enhance safety, efficiency, comfort, and connectivity, and their role will only grow as technology advances. The car of the future will not simply be a machine of metal and fuel, but a connected, intelligent system designed to interact seamlessly with both its driver and the world around it.